Hello, everyone, and welcome back to our session today. So today what we are going to do is we are going to talk about programming the stiffness method. And actually, we have covered some portion of this lecture, but in the last class, a lot of you were missing. So I want to go over this lecture again to make sure that everyone is able to follow all the important concepts. And this lecture is also important because it's related to the project that you have to do for the class. So if you have any questions about this lecture or anything else, you can always contact me, and I will be very glad to help you all. So let's get started. And what we want to do is we want to write a MATLAB code that can be used to solve like a truss or a frame problem. So we'll start with a truss programming for truss, and then we will move forward to like 2D frames and so on and so forth. So let's get started. Here, this was the truss example we were considering last time. And so this is just a generic 2D truss. I just came up with some geometry. And the important thing is we have to have some kind of a geometric information for the truss. For example, here I have given the dimensions. And there is some metadata or data for the truss we have to collect. For example, we have defined some variables in our code. We call them node degrees of freedom. So it means this variable stores what are the degrees of freedom at each node. For example, at each node for a truss element, we have 2 degrees of freedom, one in X direction, the other one is in Y direction. So it's like U and V. So 2 means 2 degrees of freedom at every node. So this variable is going to change. For example, if you have a 3-dimensional truss, then your node DOF will be 3. Okay, so when you're working for the project, you have to make those changes to make it work for an appropriate problem. And then there is another variable we defined, and this is, I'm calling it NELEDOF. It means how many degrees of freedom are there in a single element. So if we look at one truss element, each element has 4 degrees of freedom. So those are, we already know, UI, VI, UJ, VJ. So actually every element has 4 degrees of freedom. So this is the meaning of NELEDOF. Next, we label the members here. So we are labeling the nodes and members. So nodes are 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 nodes. And the elements are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The ordering of these nodes or elements is not important as long as we put a unique label to each element or each node. So what is important is you maintain a unique label. Okay, the ordering or which node is 1, which node is 2, it doesn't matter. You can change this ordering. And then we are defining some variables. One important variable is n nodes. N nodes is the total number of nodes in the structure. So in this case, we have 8 nodes. So n nodes is 8. NELE is the total number of elements in the structure. So we have 13 elements. And finally, if we know the total number of nodes and the degrees of freedom at each node, we can actually determine how many degrees of freedom are there in the global structure. So NDOF is the total degrees of freedom in the entire structure. This is just n node times node degrees of freedom. So in this case, it would be 8 times 2, 16 degrees of freedom in the entire structure. Then we created a coordinate matrix. And the coordinate matrix is actually essentially storing the coordinates of each node. So it's like X and Y coordinates in the 2D case, and it will be X, Y, and Z coordinates in the 3D case. So for now, we are just considering the 2D case, but if you're using the 3D case, just make sure to use the coordinate variable accordingly. So here I'm calling as ndim, and I'm putting ndim as 2 for the 2D case, and ndim is 3 for the 3D case. So these are the coordinate entries for our structure. So you can think like the first row is x coordinate and y coordinate for the first node. This is the x coordinate, y coordinate for the second node, and so on and so forth. For example, this fourth entry is x coordinate and y coordinate for the fourth node. So we have to fill up this entry. The next variable we created that we call con matrix, or the connectivity matrix. Con is a short form for connectivity. So what this is, what this variable is storing, this variable is storing I node and j node for an element k. For example, in this case, we have 13 elements. And for each element, we wanted to know which is node I and which is node j. So if we go back, let me go back a little bit. For example, for the first node, we are saying I node is 1 and j node is 2. And this is just arbitrary. I could have done I node is 2, j node is 1. It's okay. So it's up to us what we want to define as connectivity for a given element. As long as you pick a unique combination, it's fine. And this is the way I build up this connectivity matrix. So if we, for example, if we go up to the fifth element, so the I node is 6 and the j node is 7. So let's go to the fifth element to see what it is. So for the fifth element, I'm saying I node is 6 and j node is 7. And this is how we are building this connectivity array. And after building this connectivity array, we are going to build a ID matrix. And what does ID matrix contain? It actually contains the degrees of freedom at a given node. So in this case, the dimension of ID matrix is node degrees of freedom times n nodes. So this is the dimension of this matrix. So you can see that the first entry in any column has the degree of freedom ID of the UDOF at node k. And similarly, if you look at the second row, it has the degree of freedom ID of the V degrees of freedom at node k. And let's say that if you have a third degree of freedom, then you will have ID 3k. And that, for example, in a 3D truss, that will have degree of freedom ID of the UBW DOF at node k. Now, so this is the information we want in the ID matrix. And so if you look at, so what is happening, I'm going from one node to the next node and putting the degrees of freedom in just increasing order. So this was the first node here. The degrees of freedom are 1 and 2. So ID matrix is just storing these variables, 1 and 2. So the first node has 1 and 2. The second node, this is the second node, has 3 and 4. So this is 3 and 4. Third node has 5 and 6. So this is 5 and 6, and so on and so forth. So you can see that the columns are actually the node IDs. The first row is U degrees of freedom, and the second row is V degree of freedom. And this is the code that is used to generate this ID matrix. And you can look into the code and to see what is the logic behind it. But the code is pretty straightforward. And if you think very carefully, you don't have to change this code for if you change the for the 2D or 3D structure. This code remains the same because your node degree of freedom is going to change. So currently, node degree of freedom is 2, but for the 3D truss, node degree of freedom will be 3. So essentially, you don't have to change this code because this variable is going to change, and the size of ID matrix is then accordingly going to change. This code is going to work both for 2D and 3D case. Next, what we did is we created a variable or a matrix that we were calling as LM matrix. LM starts for location. So what does LM matrix stores? It stores the information that helps us to map the entries from element stiffness matrix to the global stiffness matrix, because we have to take the entries in a given element and put into the global stiffness matrix. So we have to store that information. For example, if we look at the element number 1, so this is the information for element number 1. So what it is actually, this is the UI. So this is UI, VI, UJ, VJ. So we are storing the degrees of freedom in a particular ordering. So we know that for the element number 1, the I degree of freedom, the I node is this, and the J node is this one. So actually what we are doing is we are just taking the I node degrees of freedom and J node degrees of freedom and putting in a column. So for element number 1, it should be 1, 2, 3, 4. So 1, 2, 3, 4. Let's say 1, 2, 3, 4, 5. If you look at the fifth element, so this is the fifth element. I node is 6, J node is 7. So the entries should be 11, 12, 13, 14. So it's 11, 12, 13, 14. And if we looked at the 13th element, that's the last element, the I node is 4, J node is 8, entry should be 7, 8, 15, 16. So this is 7, 8, 15, 16. And we don't have to manually build it. There's a code that is written. So this is the code that I have put in the Matlab file. So this code's actually build the LM matrix, that location matrix directly for us. So you can check it out that this is the right way to build the code. And the logic is you have to think about how I'm building it, but after you give it a careful thought, you will see that the logic is very straightforward. Again, you don't have to change this code for 2D or 3D structures. This remains the same because I'm not using any dimension specific information. So this code is going to work both for 2D and 3D case. But of course, the size of LM matrix will automatically change in the 3D case. And next, we are going to define some loading and support information. So what we did is we defined the variables here. So U is the displacement vector, P is the load vector. So initially, we are defining the U to be 0 and DOF 1. So all the degrees of freedom are set to 0. Similarly, for the load vector, all the degrees of freedom are set to 0. So you can think that this is U1, U2, U3, U4, and so forth up to U16. Similarly, P is P1, P2, P3, P4 up to P16. So because there are 16 displacements and 16 loads. And this is just a variable. I'm just defining all degrees of freedom are. This is the list of all the degrees of freedom. And then I defined a variable. I call it IDS. So it's an index of supported degrees of freedom. So in this case, this variable has to be initialized. For example, in this case, the supported degrees of freedom are all the degrees of freedom at node 1 are supported. So 1 and 2 are supported. And the other degree of freedom that is supported is 6, because 6 is supported here. And then 7 and 8 are supported. 7 and 8 are supported. So IDS is actually 1, 2, 6, 7, 8. So 1, 2, 6, 7, 8 is the index of supported degrees of freedom. And then I find the index of free degrees of freedom. So IDF is all the free degrees of freedom. And this is the set difference of all degrees of freedom. Subtract from all degrees of freedom, we are going to subtract the supported degrees of freedom. This is how we are going to find the free degrees of freedom. And finally, you can see that in this case, there is no support settlement. For example, none of the supports are allowed to move. So if there is a support settlement or if there is a prescribed displacement, we can go ahead and define some U values. For example, in this case, this line is commented, but we can put some non-zero U's for a given degree of freedom if needed. And next, we are defining the load conditions here. So loads are applied as shown in this figure here. So there is a load at 5, 6, 7, and 8 nodes. So these are the 4 nodes where the loads are applied. And so you can see very carefully that loads are applied in the 10th, 12th, 14th, and 16th degrees of freedom. So I'm writing here P as, so I'm just changing the P values at 10, 12, 14, and 16 degrees of freedom. So this is changed to minus 50, minus 75, minus 75, minus 50. It's important to make sure that you're putting the correct sign here. So because the loads is acting in the opposite direction to which the degrees of freedom are defined. So you have to put a negative sign here. So these are the prescribed loads here. So this is the problem setup that is needed. And so you have to do all these things very carefully. So you don't make any mistake during the coding process. Next, we have to define some section and material properties. So in this part of the code, we are trying to define the area, the modulus of elasticity, if there are some thermal effect or if there are some fabrication error. So we are defining the corresponding variables. So area for now, I'm just considering every member has area of 2, and so it's a vector of 2. So I'm just taking the 2 and multiplying with the 1's vector. And similarly, I'm assuming that every element has this number 10,000 as a modulus of elasticity. So this is the E vector. So it's a modulus of elasticity vector. I just defined some value of alpha for every member. Currently, it's not in use, but we can use this variable, or we can change this variable if needed. And then I define this dt vector. So dt is the change in temperature, and currently I'm just assuming it's 0 for a given element, and dl is the change in or it's actually the fabrication error. So I'm assuming it's 0 for all the elements. So this is all the problem data that is needed. So this is defining the pre-given problem data. So we have not solved anything. We have just defined all the data for in our code. So let me go back to show you the Matlab code, how it looks like. So this is all the problem data that is defined. So what I'm going to do is I'm going to give you these 4 files. So one is main script. The main scripts control the overall program. So this is a script, and actually there are 3 files you will find on Sakai. So this is like the name of the files are truss element force 2D, truss element stiffness 2D, and plot 2D truss. So these 3 files are actually functions. Okay, so these 3 are functions that we are going to use in our main script. So main script is going to call these functions here. And before you use any of these things in Matlab, it's very important that you keep all these files in a separate folder. So don't mix these files with other files. But sometimes what happens if you mix with other files, you might end up calling wrong functions, and all kind of things will happen. So it's better to keep it in a different folder. So you can see that I'm keeping all my code in a separate folder. So there's no other file in this folder. So I have only 4 files in this folder. So this was the problem data, as we discussed earlier: number of elements, number of nodes, node degrees of freedom. And this is NDOF, NELEDOF. So these are all the data that we discussed. And this is the coordinates. So again, I actually defined the coordinates in feet, but I multiplied by 12 to convert into inches. So this was like feet to inches conversion. So it's like feet to inches. You can directly input the data in inches, so you don't have to do this conversion, but I just did it because it's convenient. And this is the connectivity array. So you have to write down this connectivity very carefully. Okay, so make sure this data is inputted very carefully. And this is the DOF information, where the ID matrix is defined and the LM matrix is defined. So if this is done once, you don't have to actually change it, because this code is going to work for both 2D and 3D cases. And now we are defining here all the load and support data. So you can see that this is U here, this is P here, this is all degree of freedom, and then index of supported degrees of freedom, index of free degrees of freedom, and this is the load vector here. So again, make sure that you're using the right degree, you are putting the right degrees of freedom when we're defining the load vector. One way, what you can do is you can always put a breakpoint and run the code up to a breakpoint. So let's say that I have run the code up to line 55. So breakpoint, how do you put the breakpoint? Just click on this side, this panel here, and it will put a red dot. And then you can say, you can run your code and stop at the breakpoint. And actually, I can see my variable. So if I click here U, so you can see that U is all zeros. So U is all 0. It's actually, the size is 16 because there's 16 degrees of freedom. And you can also look into the problem data here. So you can see that U is all 0 here. But P, if I look at the P, P is not 0 because some of the values I have initialized. So you can see that these are initialized at the correct degrees of freedom. Okay, so they should be initialized at 10, 12, 14, and 16 degrees of freedom. So they are initialized at the corresponding degrees of freedom. So you can also check your problem data this way. And finally, these are the member and section properties or geometric properties. Area, modulus of elasticity, alpha. This is a coefficient of thermal expansion, so if it's needed if there is a temperature change. And this is the temperature change vector, and this is the fabrication error vector. And let me put another breakpoint here, and let's run this code up to this point. And finally, what I'm doing is I'm using this. I have given you this plot 2D truss function. So this function actually can plot a 2D truss just to show you the geometry. So this is a good check to just see that your geometry is correct. So if I run this problem up to the next red dot or up to the next breakpoint, I can see that this is the plot of the truss. So you can see the geometry is correct. I'm not missing any element. So this truss looks okay. And you should be able to use this function directly. You don't have to change anything in this function. And within this function, what I'm doing is actually I'm just plotting I'm taking every element and just plotting a straight line between I node and J node. So that's how I plot this truss geometry. So it's a very straightforward function. You can take a look inside it. So there is no there's no like tricks or something. It's just a simple function. And I will talk about these two variables, MF and deformed flag, later on. But currently you can put MF to be 0 and deformed flag to be 0 and use this function this way. So this function, actually, you can see that this function plots, and these are the inputs. So you have to put the correct inputs: NELE, coordinates, LM, connectivity, MF, deformed flag, and U. So it takes these values as inputs and plot a truss for you. Let's move forward and try to see how can we solve the system. So what we do is we are going to first initialize the global stiffness matrix. So global stiffness matrix is size NDOF by NDOF. So in this case, like there's 16 degrees of freedom. So this is a 16 by 16. And then we are going to initialize the PO vector. So PO vector takes into account fabrication error or temperature effect. So this is the vector that comes from every element, and we have to assemble it. So it might be 0, it might be non-zero. It depends on the problem. So we are initializing it to 0 for now. So it's like 16 by 1 vector that is 0 because there are 16 degrees of freedom in the global system. And this is a very important loop here. So in this loop, what we are trying to do is we are trying to calculate element stiffness matrix for one element and taking that stiffness matrix and assembling it into the global system. So in this case, in this loop, what we have to do is we have to go to each element. So the loop goes from k is equal to 1 to number of elements. So we go to each element, calculate its stiffness matrix. Also the force vector, if there is force vector for that element due to temperature or fabrication error, and assemble those information into the global system. So you can see that to calculate the element stiffness matrix and element load vector, like I'm calling this as KELE and POELE. So KELE is the element stiffness matrix and POLE is the element load vector that comes from fabrication or temperature. I've created a function. So this comes from a function, truss element stiffness 2D. We are going to discuss this function in a moment. So this function actually, what happens, this function takes the coordinates of I node, coordinates of J node for that element, the E value for that element, A value for that element, K means for the kth element, so for a given element. Or in this case, we are looping from k is equal to 1 to NELE. So it just goes so you're looping along each element here. And so on and so forth. Alpha value for the k element, dt value for the k element. So it's a temperature change or the fabrication error for the k element. So these are the inputs to this function. And this function actually outputs KELE and POELE. And after we have this KELE and POELE, we are going to put these two stiffness matrix and the load vector for the element into the global system. So to put this into the global system, these are the two lines, 70 and 71. So you can see that these two lines are actually assembling your system. So to do the assembly, we are just using the information in the LM, because LM actually have the information that maps from the local degree of freedom to the global degrees of freedom, or tells you where the element stiffness matrices should go into the global system. So this is the piece of code that is needed. And actually, this is written in a very general way, so it doesn't matter whether the structure is 2D or 3D, this is going to work. So you don't have to change this portion of the code. This should be working for both trusses and frames. Actually, this is a very general code. As long as you have the consistent dimensions, this assembly is going to work. So you can think about it, how the assembly is working. So this is the idea of slicing that we have discussed earlier. So let me show you in the idea. So let's say that so let's go to the first element. So if I loop through it, you can see that K is 1 now. So the first element, we get the stiffness matrix. So I take one more step. So this is the stiffness matrix for one of the element, and this is the PO vector is 0 because there is no temperature or fabrication error. And finally, what is happening? This K gets added to the KG at the right locations. So if I loop, if I take one more step, and this is your KG. So you can see that the KG values, initially they were all 0. Now it has some entries, and these entries are automatically assembled for you. So this is going to happen in the loop, and if you go through all the loop, we should be able to assemble all the entries. So let's try to assemble everything. So if we try to assemble everything, so this is the KG. So KG is now, so let me show you how the KG looks like on my screen here. So this is the KG. So you can see that this stiffness matrix is all populated with different numbers. And as long as we build the connectivity and all those data correctly, we should be able to get the right KG automatically using this process. So after we have the KG, we can go ahead and solve the system. And the solution is done using the block solution form. So this is something that we have already discussed. First, we calculate the free degrees of freedom. So UIDF is KFF inverse PF minus POF minus KFS-US. So this is the expression that we were using all the time. So, but this is written in a very compact form. With this expression, we can find the free degrees of freedom. So you can see that I'm only updating in this step the free degrees of freedom. Okay. So this is the calculation for the free degrees of freedom. So we can calculate the free degrees of freedom here. And after we do the calculation here, you can see that now the U values are non-zero. So if I show you let me clear the screen here. And if I show you the U values, now you can see that there are a lot of non-zero U values, because this is what the solution looked like. So these were some zero values are the supported degrees of freedom, and non-zero values are 1. These are the free degrees of freedom. And after we calculated the UF, this is the calculation for support reaction, or PS. So P at IDS, or the supported degrees of freedom. So this is the equation. This is KG. So we are just taking S and F degree of freedom and multiplying by UF. So it's actually KSF UF. This is KSS US plus POS. So this is a compact way of writing the solution for the system, and this statement is going to update the support reactions. So let's say that let's see. So before the update, P looks like this. So we only have the free degrees of freedom here, the supported degrees of freedom all 0. But after this update, the supported degrees of freedom will get populated. Let me again show you what does the P look like here. So now after this update, this is the P. So you can see that free degrees of freedom remain unchanged. For the supported degrees of freedom, we have some non-zero values. So these are the support reactions. So we can get the support reactions here. And after getting the support reactions, we can calculate the member forces. So when we are calculating the member forces, we want to calculate the member forces in the local coordinate system, and we'll discuss this in a moment. But you have to go back and review some of the previous lecture where we discussed the concept of local and global coordinate system. And what we want to do is we want to get just one number for every truss member. That tells us whether the member is in the tension or compression with the right value. This is the piece of code that is going to do that work for us. First, we initialize this force as zeros and any one, so it's all the forces are 0, and then we loop through each element and do the calculation for each element and get the information. And to do this, I have written one more function. So this function, what this function does it, this function takes the I coordinate and j coordinate for each element, and the properties for each element, and also the displacement vector for that element. So it takes into account the displacement vector. So um is actually ui, vi, uj, vj for a given element. And for a given element, this statement calculates ui, vi, uj, vj. So you can think that u has all the entries, but if you do lmk, so lmk means first element, the degrees of freedom. Let's say for the first element, the degrees of freedom are 1, 2, 3, 4, and if you evaluate u at 1, 2, 3, 4, this is actually what enters into So is actually u1, u2, u3, u4, and so on and so forth. So it's automatically pick up the correct degrees of freedom. So input the degrees of freedom in this function, and this function calculates the forces for us. So let me put another breakpoint and go through this whole loop. And actually now I can show you, or I can show you the variable here. Let me show you the variable here. So these are the forces. So you can see that these are the forces in all the elements. So start from 1 to 13. So we can calculate all the forces. Negative means compression and positive means tension. So some elements are under compression, some are under tension. And if you can actually also, if I click in the command window, you can see also the variable here. So these are all the forces in the truss element. One of the entry you can see is a very small number. Actually, this is like a floating point, very small floating point. So it's actually technically 0. So this number is actually 0. It's very close to 0. It's just numerical noise. Finally, what I have that function to plot truss geometry, and actually I can use this function to also plot the deformed shape. And that's where that 2 flags that was there earlier. So the meaning of this deformed flag is like this. So if this flag is 1, it means that plot both deformed and the original configuration. And if this flag is 0, it means just plot the original configuration. And magnification factor is the magnification factor that is used to plot the deformed configuration. So let me just show you. So if I say continue, and if I plot this is the deformed structure. This is both. So you can see that this the red is the deformed shape and the black is the original configuration. But you can see that because the deformations are very small, you cannot see visually how the structure is deforming. And that is where this magnification factor helps. So actually I can say that, okay, I want to put a magnification factor of 5. And actually I can just run this piece of code again. And this is, now you can see that the deformed shape is plotted with a magnification factor of 5. And actually I can see more easily how the structure is deforming. So this is how the structure is deforming in this case. So you can see that these nodes are moving down because the loads are, of course, applied in the downward fashion. And so this is the correct deformed shape of the structure. So magnification factor is just to easily visualize the deformed shape. In reality, the deformations are very small, so it's not visually like you cannot visually see it. So this magnification factor is a good it's a good device actually if you want to really see how the structure is deforming. So you can play with it and see, like, you can use different numbers. So if I put a very big number, you can see like it will look like a So you can see that, okay, you can see more like the deform effects. Okay, but always make sure, always think like that. Okay, this is when you put a magnification factor that is large. It's not the real deformed shape. It's just like a magnified deformed shape, but it's still you can appreciate how the structure is moving under a given loading. So this is the end of the code, and you can see that with this piece of code, it's not very long. It's like I have actually 91 lines of code, and actually this code can solve practically any 2D truss problem. So this is a very straightforward code, and I hope that everyone is able to follow how to work with this code and how to use this code. Now let me go over some of the important things that I have not gone or that I have not clarified yet. So one of the important function that we used was truss element stiffness. So I call this function as a truss element stiffness 2D, and so we already described the input to this function, and so these are all the inputs. And it's important to make sure that you put the input in the correct order. Okay, so for example, I cannot switch the position of coordinate j and i because this is the correct order, and so on and so forth. So order of the inputs has to be correct. Actually, it should match, the order of the input should match the function definition. So this is where I have defined the function. So this is what the function looks like. So let me go over the function, like how I created this function and what is the idea behind it. And before going over this function, I want to go back to the presentation and just revise some of the concepts. So what we want to do is in this function is we want to calculate the element stiffness matrix and the element load vector. And so within this function, we are going to use the idea of transformation that we discussed in the lecture a few weeks back. So what we want to do is we already know this is the element stiffness matrix in the local coordinate system. So bar indicates it's local, so it's a 2 by 2. And these are the fixed end forces in the local coordinate system. This is for fabrication error, and this is for temperature effects. So it's composed of two parts, fabrication error and the temperature effects. And so because we want to work in this way, because these are very easy to calculate. So we can just do a simple calculation. And after we calculate the quantities in the local coordinate system, we want to bring back into the global coordinate system, because that's the quantities that we want to assemble. So P0 is the quantity in the global coordinate system. This is just T transpose P0 bar, where T transpose, where here T is the transformation matrix, and this is the transformation matrix in the 2D case. So you can go back and look into the notes where we talked about transformation. This is the transformation matrix where lambda x and lambda y are defined like this. So lambda x is xj minus xi divided by L, where L is the length of the member, and lambda y is yj minus yi divided by L. So xj and xi are the xi and j coordinate of the, like these are the x coordinate. You can think like xj is the x coordinate of the j node, xi is the x coordinate of the I node, and so on and so forth. And similarly, the stiffness matrix, this is the calculation of stiffness matrix. You can take a stiffness matrix in the local coordinate system and do this calculation to find the stiffness matrix in the global coordinate system. So in this function, what we are going to do is we are going to write these entries, because these are easy to write, and use the transformation to calculate P0 and K. So P0 and K is actually P0 ELE and K ELE. So these are the calculation for a single element. Okay. And this is what I have coded. This is the mathematics I have put in the code here. So the code is not very difficult. So you can see that in this code, we have the coordinates I, coordinates j, e, a, alpha, dt, dl. Okay, this is very important. Okay, the order should match. So this order should match this order here when you're calling the function. So we are calling this function in this way. This order should match here. So coordinate I, coordinate j, e, a, alpha, dt, l. So you can see that I'm putting the variables in the same order. Coordinate I, coordinate j, e, a, alpha, dt, and dl. Okay. So this is important. and the outputs are KELE and POELE. The first is we are calculating the length. So length is easy because we have the coordinate I and coordinate j. So coordinate I has two components. The first component is x component. The second component is y component. Similarly, coordinate j has two components. So this is the coordinate. This is the x and y coordinate of the j node. So because we have the coordinates I and j, we can calculate the length. So length is just square root of this is xi minus xj square yi minus yj square. So this is a simple algebra. So after we have the length, I'm just calculating the stiffness coefficient for this member. It's EA by L. So this is the stiffness coefficient of this member. And then finally K local. So K local is a 2x2 stiffness matrix. So it's a simple K minus K minus K. So if I go back, this is K bar actually. K local is K bar. Okay. So this K local is this matrix here. And next, I'm calculating the temperature and fabrication error. So temperature error is alpha dt EA 1 minus 1 and fabrication error is K DL 1 minus 1. So this is actually these two vectors. So I'm calculating them separately. And then I'm finally adding them into a single vector. Sometimes you don't have to calculate them separately. I keep them separate just for clarity. Sometimes when you write a long piece of code, it becomes a little bit unclear. So this is just to make the code a little bit more clear. And P0 local is a summation of PT and PE. And when you write in a clear way, it's also easy to debug. So if there's a mistake, it's easy to figure out a mistake. Or if you try to write everything in a single line, sometimes it's very difficult to find a mistake. And then the next goal is to find the transformation matrix. I'm calculating these two numbers, lambda x and lambda y. So these are lambda x, lambda y here. So these are two numbers and this transformation matrix. So after calculating the lambda x and lambda y, because they just depend on the coordinates and L. So we already have the coordinates, we have the L, and this is the transformation matrix. So this is the transformation matrix for a two-dimensional truss. Actually, the only difference between the two-dimensional and the three-dimensional truss is the transformation matrix. So you can actually, this is the reason this is a very powerful concept. You can go back and change the transformation matrix, and this code will work for the three-dimensional truss also. So this is a key difference between the two-dimensional and three-dimensional truss, and you have to go back to the last lecture notes to see why it's like that. Okay, so we have discussed this earlier. And finally, once we have the transformation matrix, we can go and calculate the element stiffness matrix in the global system. So this is T transpose K local T, and also the element load vector due to temperature and fabrication in the global system. So it's actually POELE is T transpose PO local. So these are these two equations here. So these are the two equations here. And finally, we are done with this calculation. So we have KELE and POELE. These are the two outputs. So these are the two outputs, okay? So these are the two outputs. So this is how this function is working. And so this function is pretty straightforward. There is, I think everyone should be able to follow it. And if you have any questions, please let me know. Or if you have any confusions, like how to write a function or how to think about it, you can always let me know. So this was one of the functions that we were using. The another function was actually the truss element force. So this function is actually very similar to the truss element stiffness. So in this case, what is happening, we are still passing on the coordinates, the properties, EA, alpha, DT, DL, and the displacement vector. So this is the new variable that we are passing. This variable we were not passing into the stiffness. So this is a new variable. We were not passing this variable to the truss element stiffness, that function. And this function has to just output one number, and the output is the fourth. And I'm storing that, whatever the output, in this FMK. And so let me go back to this element, this function here. So you can see this is the function. One important thing is you can see that this is the name of the function, truss element force 2D, and this is also the name of the file. So the file name and the function name matches. Actually, Matlab sometimes complain if this is not the case. So it's always a good practice to make sure that the file name and the function name is the same. Okay, so my function name is truss element force 2D, and this is the same name here. If you see truss element force 2D, so the file name and the function name should match. If I don't match it, let me change it a little bit here. You can see that Matlab is highlighted. So Matlab is trying to say, okay, use it the same name. So okay, and so I can say fix it here, so it goes back to the original name. So make sure that you keep the same name. It's a good practice. These are the inputs. Again, coordinate I, coordinate J. So this is the XY coordinate of the I node, XY coordinate of the J node, E for the member, A for the member, alpha value, delta T, delta L, and the displacement vector. So in this case, the displacement vector is actually UI, VI, UJ, VJ. So they are 4 numbers. And this code is actually practically the same that is for truss element stiffness. So first we calculate the length and the stiffness coefficient, that is EA by L. And then we calculate K local. So K local is just stiffness matrix in the local coordinate system. And finally, we are again calculating PO local. So this is the contribution of temperature and fabrication error. And again, we are calculating the transformation matrix for that element. So this is exactly the same code. So I just copied that code in this thing, in this function from the stiffness to the force function. So difference is as follows. So what we are now trying to do is we are trying to take the transformation matrix and converting this global displacement to a local. So local is only 2 components. So actually this is so if I go back and try to show you what we are trying to do here is actually this code. Let me show you right here. This is a better way. So in this case, what we want to do is our P out is just Fj. So we want to actually give output as Fj bar. And we are giving this output in the local coordinate system, okay? So if Fj bar is positive, this member is going to be under tension. And if this is negative, this member is going to be under compression. So only one number we want to output, and the sign will tell us whether it's tension or compression. And the idea here is after we do all the calculation up to this transformation matrix, we use this transformation matrix to convert this global U vector to the local U vector. And global U vector has 4 components, UI, VI, UJ, VJ. Local U vector has only 2 components, UI and UJ. Okay, and so to review this concept, you have to go back and review the lecture notes from the previous classes. And after we have this information, UI, UJ in the local coordinate system, we can calculate the forces. So for the truss member, so forces for the truss member is P local is K local times local. So this is the contribution of displacement plus PO local. So this is the contribution of temperature and fabrication error. So we just add the contributions together. So P local is actually Fi and Fj. So it has 2 numbers in it. Okay. So P local has 2 numbers, Fi and Fj, but we want to only output Fj. So we just want like 1 output. So you can see that P out I just put is P local 2 because the first entry is Fi. So the second entry is Fj. So P local 2 is the one that we need, and this is the output here. And P out is the one that gets stored in that FM. So if I go back, P out is the output here, and this is the number that we stored in FMK for the kth member. This is the 4th value, and this is how this function is working. You have to think very carefully how to write this, but all these codes are available to you on Sakai. And so I want you to go over these codes very, very carefully and think about it. And definitely you have questions for me, okay? So after you go over these codes, you can talk to me on Google Hangout, and we are going to discuss any of the issues that you have when you go over these codes. And what you have to do is, in one of the homework is actually, I'm going to give you some problems. And what you have to do is you have to put the problem data in the MATLAB script and use these codes to solve your problem. Okay, so it will help you to understand how to use the code and how to put the problem data. So this is something you will do in this week's homework. And let me see if I missed anything. Let me go back to my slide here. No, so this was the last slide, and with this, I hope that everyone understands how to program the stiffness method. And so this is a very important concept. And so you have to take this code and extend it for the 3D truss case as a part of your class project. And I'll provide those details soon. But in the meantime, if you have any questions or any concerns, just let me know. Okay. And so this is the end of this lecture. And good luck, everyone, in understanding these concepts. And I'll talk to you soon. Bye-bye.